Thank you so much for joining us. I'm Jordan Soto, and I'll be your host for today's Hart Energy webinar, Gain Insight into Complex Emission Challenges with Kuva Systems Methane Imaging Solutions. Before we get started, we just have to go over a few housekeeping items to ensure that you have an optimal engagement experience throughout our webinar. Now, you've joined listening using your computer system by default, but if you'd prefer to join over the telephone, all you have to do is select phone call in the audio pane, and then the dial-in information will be displayed. Though all attendees are in listen-only mode, we definitely want to hear from you. You can submit your questions at any time during the presentations, during today's presenter of the information that you're going to be consuming today. All you have to do is type them into the questions pane of the GoToWebinar control panel. If the speakers are unable to address your questions during our Q&A, they'll follow up with you and address them individually. And with that, let's get started. We'll be discussing the complex challenges that occur with operations as it relates to methane leaks and how Kuva Systems Solutions can help determine what caused the event, as well as how the repair process can be expedited and how expensive false alarms can be eliminated. With that, I'm excited to introduce our speaker for today, Robert Ward, VP of Business Development for Kuva Systems. Robert, please take it away.
Thank you, Jordan. Appreciate that nice introduction. And thanks everybody for carving out some time today to sit through with us. So, you know, everything in the news and all the pressure lately has really been around methane and mitigation and detection. And what we're really finding is that the detection part's pretty straightforward. It's the mitigation that's challenging. Is what do you do with it? How do you identify it, and how do you engage, and what do you need to make it actionable? So we see from the EDF that 70% of the emissions come from about 2% of the assets. So they're really intermittent. And these are sizable emissions. These are over 10 kilograms an hour. Then the other 30%, those are kind of the pesky ones. And they're coming from about 98% of the assets. So they're all over the place. They're intermittent as well, but they're quite small. And we really think that continuous monitoring is really the way to engage all this. There's still going to be a huge demand, an increasing demand actually, for manual LDAR requirements with some of the new rules that are coming down. So the key is really to find and fix those super emitters fast. We're talking within days, not weeks or months. And some of the things that we've learned recently about super emitters is that they're hugely intermittent and really random. So an example here, if you had 500 upstream oil and gas sites, an airplane survey might see 1% to 2% of these sites that have super emitters. But of those, what you'd find, let's say that there's 10 out of those 500, is that 9 of them only last hours or days, and they're going to reoccur, but somewhere else on the site. So having eyes on the site is really key, because it's a continuous pursuit, because these emissions, they're intermittent, they're driven by process conditions, and they're changing all the time. Through our own set of data, we came up with some numbers. It's 25 cameras across 4 producing basins and over 1,000 alarms. And one of the things that we found of emissions that would constitute being a super emitter is that they only last about 21 minutes. In previous discussion with a lot of our customer base and prospective customer base had been that these super emitters that you see on Bloomberg with flyovers and that sort of thing, is there's an assumption that they last for hours or days. And, you know, we see it, we get notified and go out there with a handheld camera and try to find it. But again, those 1,000+ alarms that we looked at, they only lasted about 21 minutes. So it's really, really tough to find these things. So the EPA's proposed SERP, or Super Emitter Response Program, that's again proposed to come down this fall, is for anything that's over 100 kilograms an hour, or around 5 MCF an hour. And there'd be a notification that was sent, and then given time to find it, determine the leak or the problem of it, then fix the problem and report back, and also report back if you can't fix the problem. And these are known as cold vents, and they're things like uncombusted flares or large tank emission events. but the proposed fine on that's $1,000 a day, and it'd go back to the most recent LDAR inspection. So it could turn out to be a pretty big number pretty quick. And looking at this chart over on the right here, that's from our own data sets of cameras that have been out in the field for as much as 18 months, we see that the majority of these super emitter events are from tanks or flares. So some of the issues you get into there is there's a lot of technologies that are out in the field, and some of them are lower cost, and they're doing site-wide quantifications, but point sensors, for example, where the gas needs to find its way to those sensors, and tanks or flares are a little problematic that way because they're at such high elevation. Most tanks are 20 to 30 feet, and flares can even be higher than that. So it's really difficult to get a set of eyes on these things. You can see here, this is from the Kuva portal from a customer that's been anonymized here, but you can see the smaller calendar towards the top right, that there's not emissions on every day. The orange circle that has a number in it represents how many events there were that day. And you can see that it goes as much anywhere from 2 days to a week between those emissions, and then they can occur somewhat back to back. So the intermittency really is a difficult thing. So what we're looking at doing is taking those timestamp images, as you see here, you can see the timestamps and the duration, and take that data and correlating it with SCADA data. So this example that you see here would be, let's say that you had an Anardo valve or a tank thief hatch that had been violated and it's flowing gas. And then you have a tank pressure here that it's high. It's had a couple of events that have caused it to go high. And this valve threshold that would more likely represent a vapor recovery unit set point to turn on. So taking these timestamp events that we have here, correlating that with SCADA data, and helping our customers find operationally the root cause of these large events. So some common operational emission examples that we see, or pressure relief valve releases. So these are things you don't expect. The PRV's doing what it's supposed to, and these are pretty short duration events. You wouldn't expect a PRV to go off for very long before the condition goes back to normal and that valve closes like it's supposed to. But being able to capture that and know that you might have a maintenance event or some operational condition that's driving this, it'd be pretty handy to prevent it from happening in the future. Here we have a leaking Anardo valve, and this is really interesting. This was the first installation for a client in the Delaware Basin, and we saw the gas flowing out of this Anardo valve, and it was a test site, and there was a dozen point sensors around there, and also a scanning laser tower. And what was real interesting is that none of the point sensors were picking up the gas that was coming out of this, nor the scanning laser tower. And the only thing that we can figure kind of the cause for that is the direction of the wind and the speed of the wind. So the prevailing wind could have been a tailwind, which would have had it perpendicular to the laser towers, and the velocity was just such that the gas never had time to make it down to those sensors. So we do see opportunities where a whole range of sensors or technologies might be required to accommodate a field, but this just gives you an example on one particular site and one application where that distinction was clear as a bell. This was a pretty interesting application here. It's a corroded vapor recovery tower header. So there was gas coming out, and what was happening was, this wasn't being picked up with a handheld OGI on their Method 21 inspections. And what was happening is that due to the lack of slope in that header line, there was a lot of corrosion, and it basically looked like your gas grill that you might have in your backyard. So when the re-vapor pressures would start to build up, it would start pushing gas out of those pinholes down that header. And then when the pressure got high enough, the vapor recovery unit would come on, and then it would start drawing the gas down like it's supposed to. The other problem with that is then it starts pulling oxygen in, and what could go into a cell's gas line. So that's problematic in itself. But with the camera, we're able to see those kind of emissions. This plug flame arrestor was real interesting. We were as you'd expect, we're looking for the production tanks to be the big violators here, because the tank you saw in the previous slide, the tanks, flares, and compressors are the big emitters. We weren't really looking for the water tanks, and it was interesting to see this gas that was coming out of the low pressure water tanks. So through some analytics with the customer, working with their SCADA data, as well as a timestamp emission data that we had, what we're able to find is that when production, or when a compressor went down, production got diverted to flare, and the flame arrestor was plugged up. So it was creating a back pressure, and production was finding the path of least resistance and ended up working its way back through the system into the low pressure water tanks, violating all the hatches on those water tanks. So this is another one where with a handheld OGI, you may not be looking at your water systems for emissions, and being able to take these images with timestamps, correlating that back through all their process data, we're able to help find the root cause of these emissions. This is a pretty interesting condition. It's an unlit flare. These are unlit flares are big super emitters, and one of the things that makes flares really difficult to find when they're not properly combusted is that the elevation of the burn is up high. So a lot of sensor technologies are not going to pick up on that. The other thing is that because of previous EPA rules, operators generally monitor the temperature of the pilot, not the combusted end of the flare. So in this condition, the pilot was reading 1250 degrees or something like that, which it was supposed to have been, but we're showing that the gas was uncombusted. So what's happening here is that we're seeing a shadow that's being cast down of the uncombusted gas. And that's what you're seeing with the red, blue, green, and the yellows there. And the image that shows just the two little blue spots is where the igniter tried to restart the flare, and then it would get blown out again. What it ended up being the root cause of this particular application was that this is a forced air blower assist flare, and the system was designed for the initial production rates of the facility. But as the asset had gone into decline, the production had gone down, and the blower was sized such that it wouldn't turn down any lower. So it would continue to blow every time they would go to flare, the blower would blow the flame out. So it ended up being an issue that took a little bit to find the root cause, but in doing so is able to mitigate future emissions. And here's just another one with the RGB image going on here. And then truck loading, you kind of expect to see this. A lot of lines now are tied to vapor recovery, so a bunch of this can be mitigated on the fly, but it does give you an idea of what's going on when an operator's there. And one of the things that we really work hard at is trying to help our customers minimize alarm fatigue within operations. So the goal is to take the image data that you're seeing here and put it into the workflow of the operators, so that this is part of their everyday life. It's not something that's an exception. And where a typical sensor, another sensor type that is not image-based, there might be an alarm or notification that would require somebody to jump in a truck right out to the site and see what's going on. By getting a notification like this, you're able to tell that there's an operator that's on site, and these emissions are part of the work process. They're not an exception or an emission event. This application here was quite interesting. It was the first day of this camera being installed, and we had these emissions that were coming off the tank tops. So we're able to work with the customer that afternoon and get a copy of, see what the SCADA data look like. So this graph that you see here on the left-hand side is from their SCADA system, and it's ranged to about 16 ounces of pressure for reed vapor pressure or tank vapor pressure. And everything within the SCADA system appeared that they should not have these emissions. So what we're able to find is that by going out to the field and simply zeroing the pressure transmitter, they were able to mitigate these emissions. The transmitters had been installed out of the box and not zeroed to local conditions, and just that little bit of zero offset was enough to cause these emissions. And by properly zeroing those transmitters, they were able to keep the system from violating those defhatches. So we're really looking at extracting more value with partners and integration as we've opened our API so that we can plug into other systems now. So Technip FMC, some of you may be familiar with, they're a global company. They have a strong presence here in the Houston area, and we're working with them on an application that's really an active methane mitigation. It's called emission. And this system that you see here has been installed for 4 to 6 months, and they've been able to realize a 55% reduction in their flare activity and also a 1% increase in production. So what they're doing is with their black box, some edge compute, they're getting data pushed directly from the SCADA system or the local PLC at the facility, and they're tying our timestamp data, emission data from the cameras into that system and finding the correlation between read vapor pressure and emission activity, and then optimizing all the processes around that so that they can contain as much of the product as possible while at the same time mitigate emissions. So the way that we do it, we have our camera, and this is a real camera sitting here behind me as well. So we have our camera that's installed at height out in the field so that we can look down on the processes. So typically 30 to 40 feet installation height. And we also provide this tower that you see here. It's non-ground penetrating. It can be installed in just a couple of hours. The camera runs on 24 volts. It has a capability to rotate 360 degrees. And of that 360 degrees, we make 270 of it available for customer viewing so that you can see the majority of your processes. From the camera, we can see out in typical and more ideal applications out to 100 meters or about 360 feet that we can see from the camera. So it gives us a really good reach. So customer can select on deployment if you want either 3 or 6 fields of view that are 45 degrees each, horizontal, and 50 degrees vertical, letting you see everything from the tank tops and many times the flares, all the way down to what's happened with process piping, metering skids, and that sort of thing. And it only takes between 30 seconds to 3 minutes to scan the whole site, all 270 degrees. So update time is not hours like you might have experienced with some other technologies. So the way we do it is inside the camera, we have our proprietary shortwave infrared sensor. We also have a visible RGB camera so that you can see what's going on. We have the edge compute inside the unit that's running Microsoft Azure's IoT Edge. We have integrated communications so we can connect LTE, or we can plug directly into our customer's field communication network. We just need an internet connection. We do have the motorized 360-degree pan stage so that the camera does rotate on its own axis. And then we have an anemometer that you see up top. And that ultrasonic anemometer gives us live wind speed and direction, which is important in the quantifications. So from there, the camera creates candidate images. They go up to the Kuva cloud, which again is Microsoft Azure. And then from there, it goes through other filtration and algorithms so that we can do false alert or false alarm mitigation. Then we're also doing quantification there. And then our customers can log into the portal. They get notified based on the criteria of whatever constitutes an alarm or notification for them. And then we can also take that data and make it available via API or a webhook so you could tie it into your SCADA system or a Historian, work order generation, and then also take that data and feed it into regulatory or reporting frameworks like OGMP 2.0, MIQ, Project Canary's TrustWell, Valideer, the list is long. Anyway, there's that whole environment of platforms for recording, reporting, reconciliation is growing on a daily basis. From a technical performance perspective, our camera was at METEC, Colorado State University, north of Denver a little bit. And METEC runs this program called AIDED, which is Advancing Development of Emission Detection. And this program lasts for 5 months. It runs 24 hours. They have big leaks and small leaks and short leaks and long leaks there. When there's a lot of wind or no wind, a lot of sun, little sun. And what they're looking for is probability of detection for a given technology. And that probability of detection is actually a 90% probability of detection. So that means if that situation occurred 10 times, a technology would pick it up 9 out of 10 times. So how small would, or how sensitive is the technology in those conditions? They also look for a false positive rate and then the ability to pinpoint the source of the leak. So from there, we were determined to have a detection limit of 3.5 kilograms an hour. And we had 0 false alarms. So through hundreds of controlled releases, all blind releases, we had no false positives. And we had 100% pinpoint accuracy to the component level, not to the equipment group level, like a set of tanks, but the actual tank, which thief hatch was it, so that you know which piece of equipment to go after. So in that space with other technologies, there were 11 technologies, 5 of them were cameras and 6 of them were point sensors. Of the other cameras, which were multiples in cost for installation and cost of ownership, the performance ranged from 3.7 kilograms to over 10 kilograms an hour. They had 10 to 20% false positives, but they were also around 100% pinpoint accuracy, so similar to ours. And then on the point sensors, as you'd expect, they have greater sensitivity, but there's also, as you'd expect, 20 to 50% false alarms or false alerts. And the pinpointing accuracy was basically none on that. We do believe they'll be getting better over time, but for last summer, that was the test results. So the false positives is something that we spend a lot of time on, and that we really focus on improvement and take a lot of pride in that, because we talk to our customers and nobody is overstaffed at this time. They're all trying to figure out, how do you integrate with workflow? How do you keep from having to respond to these smoke detector type alerts where somebody has to stop what they're doing and run out with an OGI? By getting an image that's actionable, that's timestamped, that shows where the gas is coming from, a decision can be made pretty quickly on what needs to be done. So on that probability of detection, this gives you an idea. You can see what the performance curve here is, and the paper is publicly available from METEC with all of the participants in there. And one of the things that's quite unique is how tight the bands are of all the detections that you see there. And again, our 90% probability of detection of 3.5 kilograms is pretty great. And that's at about 20 meters distance. And over on the lower right-hand side, you see there the green dots are showing the equipment that was being released, and then our ability to detect which piece of equipment was the source of it. And again, all of that with no false positives. So a little about Kuva. Sorry about that. We're December, we turned 7 years old. We have 50 some odd employees. We're based in the Boston area. We do our manufacturing there. We are actually made in the USA. We have offices in Houston, where I reside, Calgary, and also in Denver. We're founded by some guys that were working in the defense industry. We have a strategic partner and investor that some of you might recognize the name, a German outfit named Draeger. They're a world leader in point sensors and gas tube sensors. So we have around 150 cameras deployed across 20 some odd operators, both upstream and midstream. We're in northern and southern Alberta and British Columbia. We're in North Dakota's Williston Basin. We're in the Stack and Scoop in Oklahoma. We're in the several parts of the Permian Basin out in West Texas, New Mexico. And then we also have cameras deployed around the Eagle Ford Shale in the NGL region, the dry gas region, and the oil region. So we kind of cover that shale pretty well. So with that, that's kind of a quick pace through the technology, and I would love to open this thing up to some live Q&A here.
Thank you so much for that presentation, Robert. It was so much in-depth information, and I really feel like I learned a lot, and I hope you did too. As Robert said, it's now time for our Q&A portion of this webinar, so we're opening the floor up to Q&A. As a reminder, you can submit your questions by typing them into the questions pane of the control panel. And we actually have our first question in already. So Robert, what should our operators, this is what somebody's asking, is what should our operators and environmental managers be doing to prepare for the upcoming super emitter response program that's coming out in August this year?
Well, I think getting a handle, finding what part of your operations are really the emitters. What's the intermittency? What's baseline condition? What's exceptional? What are the process conditions that are creating these emissions, so that you can better mitigate and basically take an active approach into mitigating those emissions. I think a lot of people think, oh, we have some emissions, let me grab some wrenches, I'm going to go tighten some bolts. And that's really not the case. The majority of these emissions, especially with their intermittency, are driven by process conditions. Unfortunately, the wells, no matter what kind of controls you put on, they're going to have some variability to what's going on, and there's going to be some tuning and tweaking that needs to occur. But what you can find by taking a look at that timestamp data and those correlations is that there generally are a couple of root conditions that with a little bit of work, you can cut those out of your system.
Fantastic. We have another question here. They want to know if you could expand on how your solutions help operators more quickly repair a leak.
Yeah, sure. So a lot of there are some technologies that provide a notification that there's some gas out there, and it might be coming from this direction. But with that intermittency that I was talking about, especially with an average being 21 minutes or so, is that by the time someone gets notified and then gets out to the site, they've got their handheld camera and they're looking around to find where that is. You're really rolling the dice if you're going to be there on site while that's occurring. So to be able to get a notification on your phone or computer and have a picture of the piece of equipment showing the gas where it's leaking, and then taking that and then figuring out what process conditions correspond, what might have created that leak, then it allows the operator to address it pretty quickly and with a high degree of certainty.
Yeah, it definitely seems like it creates more of a seamless workflow. Our next question is about false alarms. They say that they see a lot of false alarms which are painful to respond to. So how can you better explain how Kuva Systems handles that?
Yeah, so the candidate image is created inside the camera, and then it's sent to the cloud where it's further processed. And then before the notification comes out, which can be, minutes, it actually goes through a human review process so that it can be validated. So as we better train, if you call it AI or ML, as we better train to shorten that cycle up, we're doing it with a high degree of confidence, so that when someone gets a notification, there's certainty that something's going on there, and we're providing an actionable image to go along with that as a piece of evidence.
Our next attendee wants to know why it's not good enough to just use planes and LDAR programs.
Oh, that's interesting. Yeah, but between those two, you really run into the whole intermittency thing. So how frequent are you going to fly a plane? Most operators are anywhere from once or twice a year, maybe quarterly. Are hearing of some people that are doing some monthly flyovers now. They come at a cost, so you want to make sure, you know, an operator would have to do the math and see what the density of their assets are like and how many sweeps they would have to make. And then with the LDAR plan, those are done on a periodic basis depending on the production or the size of the asset and the complexity of the asset. And again, those are going to be done, someone has to be on site with that. And with the handheld LDARs, they have to be on site with it. The wind has to be below a certain speed. There's a number of conditions. And that also means that they're not out doing something else. They're there looking to see if there's something going on. Whereas a continuous monitoring solution provides a high degree of certainty that, hey, we've got your back. Even when you're not there, we're providing evidence that either everything is okay or you might want to come here as soon as you get a chance because there really is something going on. I hope that answered that.
I feel like you did, but if you need further clarification, all you have to do is reach out and type that question into our control panel, and hopefully we can give you a little bit more clarification on that. But I feel like that was a really well-rounded answer. Our next question is, it goes like this. The program we use today uses point sensors, and it shows approximately where the leak is occurring, but since OGI is more expensive, what's better about
it? Well, I think there's probably a little bit of assumption that this continuous solution is the same price point as a handheld OGI solution, and it's not. It's a fraction of the cost. So there's that. I would say that to have our camera out on site continuously is near the same price point as a high-end blind point solution. And then I guess one of the big differences is that with the camera, and we have a number of customers that use a camera in conjunction with point sensors. So there's not really a silver bullet. It depends on the complexity of the site, but the camera does provide evidence of this is where the gas is coming from. And generally a point sensor solution is not going to capture tank tops. It's not going to capture flares and many times compressors. And also the wind has to be blowing above roughly 4.5 miles an hour and less than about 22 miles an hour for the gas to get to those sensors. With our camera, the wind can just be stagnant. A gas plume can just be kind of hanging there over the tank battery, and we'll see it.
So staying in line with OGI, and I believe we only have time for this last question here. In side-by-side beta testing of OGI and point sensor, I've seen where OGI saw the leak, but point sensor did not. Can you explain why?
Yeah, one of the conditions like at the tanks and flares, so a point sensors are typically installed 1.5 meters to 2, so 4.5 to 6 feet above the ground. And if the tanks are 20 or 30 foot tanks or vapor recovery towers, or it's a tall flare, not a short combustor, then many times the elevation is going to be wrong. So the point sensors will be looking for gas at a particular level to be brought to it so that it can sense it. Whereas our camera is looking out, sweeping across, and we're at 40 feet and we see down to the ground level. So we're taking 45-degree segments and we're seeing everything that's going on at that asset, regardless of elevation and regardless of wind speed up to some point. And we can see at higher wind speeds. It's just that it impacts sensitivity like it does for all technologies.
Fantastic, Robert. Well, I think that's all the time that we have for our Q&A. Again, if you're an attendee and you have a question that we didn't get to, all you have to do is submit that into our questions pane of the control panel. And we can also send that to your we can also respond to your contact info that you send in as well. Thank you so much for joining today's Hart Energy webinar featuring Kuva Systems. I hope you enjoyed this discussion and learned a lot. I know that I sure did. And if you'd like to rewatch this webinar, the on-demand session will be available to you next week. Thank you so much, Robert, and all of our attendees, and have a fantastic day.
Thank you, Jordan, and the whole staff at Hart Energy there. You guys have been great, and appreciate everybody for your time. Look forward to meeting you.